Let's get started again here with a little conversation. I'd like to try to do a little deeper dive into some trigonometry, as in a nice topic to explore, a little conceptual work here that kind of bridges pre-calculus to calculus. So we're really going to be doing some calculus without doing calculus. We'll get into it, and hopefully 10 minutes from now, you understand the comment I just made. This is not a discussion. Well, I don't know. I don't know if it's helpful for somebody who hasn't had any trig before. I'm assuming that if you're looking at this video, you've done some trigonometry. All right, and I'm going to build on some of the things that you might have heard, and hopefully give some explanations as to what's going on as we move forward here. So we got a unit circle. I use my lanyard. Let's just look at a triangle very quickly, right triangle, right? And you're used to measuring angles in degrees. If I made a circle, well, then I could talk about the arc length right here is exactly the same as the degree measurement. I mean, I could use either one as a tool to talk about the ratios, sine ratio, opposite over hypotenuse. And in the unit circle, that's a 1, right? So we do have some altitude divided by 1, some altitude divided by 1 in the unit circle, and that altitude is representing the opposite side length. And when I divide by 1, then that actually becomes whatever this angle is, and that's the sine of that angle, okay? Again, I'm assuming you've done quite a bit of work already with trig when you are looking at this. Okay, so I'm not sure if you understand what a radian measurement is, so let's talk about it briefly here. So radian obviously comes from the word radius. So I've got my lanyard. Let's see, which way did I do this? I guess this way. All right, so I took the time to, do a pretty decent circle with the aid of the lanyard. And so this is 1 radius length. When I wrap it along the circle, then that right there becomes 1 radius length on the circumference. And if I make that distance my x-axis, then this is 1 radius length. Another one takes me over here somewhere, right? That's 2 radius lengths. A third one, yeah, that's pretty close. A third one might take me to there. And, and hopefully you can see that that might be 3.14, halfway around the circle. All right, because if we look at circumference, which is 2 pi r, and if the radius is 1, then this is 6.28 radius lengths all the way around. So that would be 3, 4 would be here somewhere, 5 would be here somewhere. Let's see, I knew what that, I think 5 is maybe here. Well, no, probably a little further. All right, 6 would take me to here. That much I'm sure of. Okay, so what I did is I did 1 radius length, 2 radius length, 3, 4, 5, and 6 as the x-axis. And so I will label it radius lengths. And if I want to say it more succinctly, then I'll say radians. Okay, that's my x-axis. Now, how do we evaluate trig functions? Well, we do 1 radius length. We draw the right triangle, we draw the perpendicular, and that gives me a ratio of opposite to hypotenuse. And I might as well take that right now and say that if this is 1, then the sine of the angle, whatever this angle is in degrees or radius lengths, same thing, doesn't matter the size of the drawing. 1 got me, in this picture, that altitude. I'll just draw a dot. Okay, that's a point on a curve. And then if I did 2 radius lengths, so I got to try to do this well. So let's see, I had that. Okay, it should be a little higher, that's 1. So let me just move it up a little bit. 1 would be about there. Like right above that, pretty close. 2 radius lengths. Okay, oh boy, this is the first time I've done this. 2 radius lengths would be, maybe here for a height at y value. So that's a little higher. 2 radius lengths is here, right? And the highest one I get is, let's see, let's measure this circumference. Right about there, right about there. The highest one I get is that, and that's obviously 1. That's obviously 1, which is right about there. And 3 takes me back to very close to 0. So 3 is just a little bit above, right? So it's right about there. And 3.14, it has no height. That's about 3.14, I think. And I don't know, hopefully you can see that, oh, we have created, I kind of missed it over here. We've created that, right? Not to belabor the point, but that process continues over to here. How close did I kind of butchered that. Let me just get this height. Ooh. Okay, so I'm never going to get below here. So I should take more time with this. Close enough. Okay, now we're going to head towards calculus in a second. So that's obviously 1 revolution of the sine curve. That doesn't look too bad from here. A pretty decent job. All right, so let's start talking about trig. Just for another few seconds. There's only 2 things you do. I give you an angle, you give me a ratio. I give you a ratio, you give me an angle. Well, when you start getting into calculus, there's really only a couple things you do. For the most part, I give you a rate, you give me an amount. I give you an amount, you give me a rate. So I want to talk about rates of change of what's going on here. Okay, so what do we have? 2 things happening. I'm moving around the circle. That's an operation. And I'm looking at the altitudes in the unit circle for the sine function. That's what I'm doing. And a rate of change is a comparison of the changes on both sides of that table. So if I'm moving around the circle, I'm moving in the positive direction on the x-axis. And my altitudes are also moving in the positive direction until I get here. Then my altitudes are negative. Okay, keep that in mind. Now let's actually blow up this section of the curve right here. Just that section, all right? I'm drawing altitude, so I'm going to blow this up. I don't want to put too much on here, but I'm going to blow that up and zoom in on it. That's what calculus is. It's taking a microscope, looking at things more closely. And there's actually a little bit of, so this is no distance, no radian distance, but then that starts to happen. Okay, now here's an altitude. That's my y values. So if I looked at the change in y over the change in x, and the change in x is the circumference change, I get a, boom, 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 to a little bigger distance. Okay, there's certainly they're not too far apart, but what happens as I head to 0? What happens to the, I don't know if you can see this, but if I really look at that, that's almost a 1-to-1 ratio. That's about the same distance as the altitude as I get close to 0. Okay, so let's actually see if I can get another marker here. Well, I'll use some about boxes. I'll use boxes to represent the rate. So what's the rate at this place? The y value and the arc are about the same. It's actually 1. So I'll plot this. So right there at 0, I have a rate that's pretty much 1-to-1. Well, let's go over to this side. Let's go over to this side over here at pi at 3.14 radius lengths. Well, so let's look at right there. Let's zoom in on that. My arc length starts to do that, which is still moving in the positive direction, right? I mean, I'm moving on the x-axis. That's in a positive direction. I know it looks like I'm going down and up and down, but I'm talking about distance from zero. It's just getting bigger. Okay, it's just getting bigger. 1 radian, 2, 3, 4. So this is a positive. However, my altitudes are what? They're negative. Those altitudes are negative. Now, as I start to get closer and closer and closer for altitudes, can you see that I have an actual negative 1-to-1 ratio? So at 3.14, I have a negative 1 ratio. All right, let's look at the top here. Let's look at the top of the circle. How are your y values changing there? Let's just draw some y values. Here's one right there. Takes me to this spot. That one, let's connect them. Oh, I don't think my y values are changing at all. They're basically the same height right up there because this is pretty flat right here. That's pretty flat. So yes, I am changing my circumference. My circumference has changed. Yes, so my change in x exists. But the change in y, pretty darn close to 0. And 0 divided by something is 0. So it looks like it happens to be right about here. I've got myself I'm doing boxes, a rate of change. And so I've got 2 axes here. One is about the rate of change. Then the other is the actual ratio. So I'm sharing an axis here. So the rate of change, and if I did this, I'd actually get a shape like that. I'd actually get a shape like that. And then it would come back. I'm going to miss this. I think it's close enough, right? I don't know how high I am. Hopefully that's close enough. That's a little too high on the right. Okay? And this measures the rate of change. Now, the cosine actually measures the width of these triangles, right? So you got a triangle, that's the sine of the angle, that's the cosine of the angle. So as I move towards 0, I have no height, but I definitely have a width of 1. Oh yeah, 0, 1 was the, that seems to match up with the rate we did just a minute ago. And if I look straight up and draw a triangle, I can't draw the triangle because it has no width. No width, 0, there's no width. And that's at pi over 2, which is 1.57. Oh, roughly 1.57, which is between 1 and 2, a little bit to the right. Oh yeah, that box has a y value of 0. Oh yeah, the cosine of pi over 2 has no width. And the rate, therefore, because the y values aren't changing, there's the rate. And over here, what is the cosine? The cosine over here, oh, -1. Oh, the rate, -1. Oh, geez, does it look like this graph is going down at 1-to-1 right there? Does it look like maybe over here the sine function is going up at 1-to-1? Because the altitude and the arc length are identical there. So when I compare the little bit of change to the little bit of change, it looks like it's 1-to-1. Whereas over here, it looks like it's -1-to-1. That arc length, that altitude, as described by the slope of the tangent here. Interesting. Interesting. It doesn't look like the y values are changing much here, right? Y. But the arc length is changing. So we're back to the same discussion here. Oh yeah, 3/4 of the way around. Cosine of 3 pi over 2 equals 0. You know, I think the cosine function is telling us a lot about how the sine function is changing. Kind of interesting. Well, wait till your calculus class. Of course, I'm sharing this with my calculus class right now as another perspective on derivatives. Okay, so there's my spiel. The first time I've actually laid it out here. So repetition's my friend. I suppose if I make 6 or 7 or 8 more videos here, I'd say it more clearly, but I hope I've stimulated a little thought. And, you know, we've looked at this from different perspectives, and this is just another little layering. Oh, layering, accumulation, integration, layering. Geez, maybe that layering might mean we're accumulating more knowledge. All right, I'm going to make another video on precalculus to calculus polynomials, just for posterity's sake. Nothing new. You've heard it in class, but sometimes you need to hear things more than once, or twice, or 3 times, or 4 times. Hey, I'll give you an example of that right now. A little trick of the trade. Okay, so I'm going to come over here and do a little trick of the trade because we do integration a lot, and sometimes some of the values you get are things like this, things like 2 minus 3/5. Oh, let's make it a little more challenging. Let's say we have 11/5 minus 2 minus about 4 plus 17/3. That might be too big. Let's make it 7/3. Let's do 7/3. Let's make it minus. There we go. So you get things like that, right? And I used to do bingo, bango, bongo. 2/3 plus 5/7, right? Bingo, 14, bango, bingo, bango, 15, 3 times 7, 21. That's pretty quick and easy, right? Bingo, bango, bongo. Well, I was just thinking about it. There's actually a quicker way to do fractions. Any thoughts on what the quicker way to do fractions are here? You know, what's the difficulty with fractions? Division by 3 and 5. Well, let's get rid of it. Let's get rid of it. Let's multiply by 15. I multiply by 15, I get 33. I get minus 30. I get minus 60. And I get minus a minus plus 35. I think I get that. So that's 3. That's 38. Minus 60 plus 38 is minus 22. There we go. Okay. Almost done. What do you think I should do now? Well, if you said you made it 15 bigger, it brings it back, you'd be right. Okay, so I said that because, you know, I just started thinking about that the last couple of days, and how long have I been teaching math? I should have been using that technique 40 years ago. All right, but I send it your way so that if you're doing a lot of fraction work, get rid of the denominator, bring it back in at the end, and hopefully I didn't make a mistake there. All right. Oh, got to end the video. Ciao, ciao.